and the group of transformations in phase space which preserve the structure of the Hamiltonian equations of motion. These are all very, very old classic topics, but I suppose it is always good to refresh our minds and understand things better. So, I would like to begin by writing in a schematic way the relationships among the three forms of classical dynamics. The Newtonian equations of motion, as we have seen, are usually stated for using Cartesian vector variables for the positions of this of particles in a multi-particle system. Usually this is how it is done. Then we have seen the structure of the Lagrangian equations of motion. They are sometimes called the Euler-Lagrange equations of motion. They are more flexible than the Newtonian version, and while initially the Lagrangian formalism is set up having in mind a non-relativistic system of many particles, as I have mentioned many times, this approach is capable of wide generalization. As I have said, it can go beyond non-relativistic systems, it can handle field theory, it can handle Dirac equation, so many things it can be generalized. So, it is a very powerful approach to the problems of mechanics. The next is the Hamiltonian form, which I think we looked at very briefly yesterday, the Hamiltonian equations of motion, and we will see today that this is even more flexible than the Lagrangian form, in the sense that the group of transformations which preserve the Hamiltonian form of dynamics is a much larger group than the point transformations which we saw in the Lagrangian case. Incidentally, is any one of you particularly keen to have the AC on? I do not mind if it is switched off. If it is okay. Yeah. And as we will see, there are many new geometric features associated with the Hamiltonian form of dynamics. So, I want to develop this in a systematic way. Some other terminology for the usual kinds of non-relativistic systems, the Lagrangian equations of motion are ultimately a system of second order ordinary differential equations with respect to time for the generalized coordinates. So, to reflect this, the Lagrangian method is called a second order dynamics. The idea of ultimately having to solve second order differential equations. So, correspondingly, the initial conditions needed to find a solution of the Lagrangian equations would be initial coordinates and initial velocities, generalized coordinates and generalized velocities. On the other hand, for a system with a given number of degrees of freedom, while the Lagrangian approach uses that number of generalized coordinates, one for each degree of freedom, the corresponding Hamiltonian treatment uses double the number of variables. For every q, there is an associated momentum p. So, this is very similar in spirit to what Shamik has been doing in his lectures. The equations of motion in the Hamiltonian form are first order ordinary differential equations. So, this is described by saying that it is a first order dynamics. And actually, the general idea of dynamical system which Shamik has been developing is basically a first order dynamics, forgetting about a Hamiltonian idea, forgetting about phase space, forgetting about even dimensions and so on. On any manifold, you can say any set of variables, given a vector field of suitable with suitable properties, you can have a dynamical system. All the equations of motion he has been using are first order in time, and so they are typically first order dynamics without all this prior structures being involved. So, what I want to convey to you today is how rich this form of classical dynamics is. Historically, it has played the most important role of being the stepping stone from classical mechanics to quantum mechanics. And everyone, three people by independent efforts invented quantum mechanics: Heisenberg, Schrödinger and Dirac. Heisenberg, Dirac and Schrödinger, in that sequence I should say. Every one of them used some features of the Hamiltonian form of classical mechanics, and that is why it is very important. The other thing I would like to mention in passing is that while the equations of motion in phase space were formulated by Hamilton, the person who developed this, all the geometric features of Hamiltonian dynamics, idea of canonical transformation, idea of preservation of the form of Hamilton's equations by canonical transformations, all of this was largely the work of Jacobi. Okay. And this is in his famous 1847 lectures, which in English translation, as I told you, been printed by Hindustan Book Agency. Okay. So, now I want to start with the Poisson bracket. You remember, so let us put it this way here. The Lagrangian description, equations of motion, is based on a given Lagrange function. And then we have seen how to go from the Lagrange description based on variables q and velocity q dot to the Hamiltonian description. It involves setting up a function of explicitly dependent on coordinates and canonical momenta. It is the Legendre transform of the Lagrangian. And you have seen that we are able to write an equation of motion for any function of the coordinate and momentum variables using an expression called the Poisson bracket. And you remember what this is. It is a sum over the various degrees of freedom. This is the expression for the Poisson bracket. Of course, the subject is so old, I do not know all the historical details about it. I am not quite sure in what context Mr. Poisson introduced these expressions. I do not know, but anyway, I have learnt it in this way. Okay. So, this Poisson bracket idea will become very important, and as you know, it was Dirac who discovered in September 1925 to be precise, that the Poisson bracket of classical mechanics leads to commutators in quantum mechanics. This was his very great discovery. He often said it was his most favorite discovery. So, it will, as I said, turn out to be a very important concept. Any function?
Any function of f qp is related to the Hamiltonian in this way, f df.
Not related to. You take any function of the coordinate and momentum variables and you ask, while q and p obey the equations of motion and keep changing in the course of time, how does f change in the course of time? And the structure of Hamilton's equations allows you to write explicitly an equation of motion in time for any f. It is not related to h, f can be anything. H determines the way anything changes in the course of time. Okay, all right.
So Q and P has to follow equation of motion.
Pardon?
Q and P has to follow equation.
Of course.
Means it is only for that stationary path
Yeah, of course. I mean, what is dynamics? Laws of motion obeyed, found in nature. And so, you know, because classical mechanics is such a formal subject, so much of it seems like mathematical manipulation and algebraic steps, one tends to think that actually classical mechanics is a part of mathematics. I just want to stress to you, the starting point is experience of nature, experimental knowledge. What experiments Galileo did, Huygens may have done, Descartes may have done, the way the laws Kepler found for planetary motion, none of these are results of pure thinking. I want to emphasize this to you. They were all the results of observation of nature. And what Mr. Newton did, I can't resist remembering old amusing incidents from my TIFR days. There was a colleague of mine, senior to me, Virendra Gupta. I don't know if he was there. He would always say, Shri Newton. So, what Shri Newton did was to take the experimental results found by many others and himself also, and the theoretical ideas which people had put forward to try and explain the experimental results into a coherent starting point. There were aspects of Newton's work which were questionable, which were not completely convincing, and later people criticized him. Leibniz criticized him, then there was a Bishop Berkeley who criticized him. So many people criticized, they did not agree with what he had done, but the way he had stated it. But at Einstein, he is always so balanced in his judgment. He said, forgive me, Newton, for my criticizing you, something like that. But you did the only thing that could have been done at that time, so that after you, others could do further work, make further progress. Of course, criticizing what you did, but you had to have a starting point. And this, I think, I want to convey this spirit to you. So, classical mechanics, you can say, the physical foundations were laid by Galileo and Newton. Newton laid out the formal mathematical description of it, but don't ever think that this is part of mathematics. It is expression of physical laws. In the case of electricity magnetism, the situation is much more clear. We know, and it is somewhat more recent in human history, the experimental results found by Coulomb and Ampere and Faraday and so on. None of those were results of pure thinking. They were actually results of experiments done in the lab. And what Maxwell did was to express those experimental results in a mathematical form, using the concept of a field which Faraday had thought of. And that concept of the field was one of the greatest conceptual achievements. But why was it created? In order to express in a compact way the results of experiments. So, in the case of, do not mind my wasting a little bit of time, in the case of electromagnetic theory, we have no difficulty in appreciating that Maxwell's theory is not a part of mathematics. It is an expression of laws found in nature through experiment. When you make that statement, you have to add, in principle things could have been otherwise. In principle the laws of nature could have been different, but they happened to be what was found by all these people, which was then written into a consistent system of equations by Maxwell. In the case of mechanics, because it is 150, 200 years older than Maxwell's work, there is a tendency to think this is how nature has to behave. Please avoid that way of thinking. Everything that Newton did and Galileo did and formalized was an expression of results found in experimental work. Again, you have to say nature could have been different, but they have found that it is acting in a certain way, and all we are doing is describing that way of behaving. Okay? So, this is a long answer to your comment. Yeah, of course, Q and P obey these equations of motion. We are examining the way a system develops along a path in configuration space, for example, for which the action is a minimum. Okay? So, even Hamilton's action principle, the use of configuration space, all of it has a strongly mathematical flavor, but never lose sight of the fact that all this mathematical statements and machinery is in order to express and analyze results of experiment. Okay? That is what I want to emphasize. So, now this Poisson bracket has many important algebraic features and some differential features. So, I will just list some of them. Here is the expression for the Poisson bracket between any function f and the Hamilton function. The Hamiltonian for a given system has a special role. Of course, you can replace h here by any general function g and put g in place of h on the right hand side. So, you will get an expression for the general Poisson bracket of two functions f of qp and g of qp. So, you write it down from here, replace h by g. So, the first set of properties is the following. I think you have all done this. So, what is the Poisson bracket of a q with a p? Just to make sure that these days the phrase is we are on the same page. I would just say you are following me. What is the bracket of a q with another q? How much? 0. Okay, clear. It's surely the same with a p with a p. And what is the only non-vanishing Poisson bracket? A q with a p. Yeah? Yeah, it's a Canonical delta. So, every q has with its p a Poisson bracket value 1, with any other p it has 0. Okay, this is the first set of properties. So, these are often called the fundamental Poisson brackets. Okay, these are trivial from the definition. Second is pair of algebraic relations. One is the statement that the Poisson bracket of two functions f and g is antisymmetric under interchange of f and g. So, strictly speaking, one should say this expression is the Poisson bracket of f with g. Some such statement English must be used. It is not good form to say this is the Poisson bracket of f and g. that conveys the meaning that it is symmetric in F and G. It's not true. Okay, it's just a minor point of terminology. So there is this antisymmetry property, and then there is a linearity property. If F1, F2 and G are three phase space functions, C1 and C2 are numerical constants, this is the way in which the Poisson bracket behaves. So this is called the linearity, and the first part is the antisymmetry. There is a third part called the derivation property. It is the following. Suppose you take three functions f, yeah, beg your pardon? Well, combine that linearity with this antisymmetry, what can you say? Is it linear in G or not? Yeah, but you switch it again. Suppose you want to calculate, your question is a good one. Suppose you want to calculate this one. First I will use this, I don't have to, but just for your sake, I bring it here, put f there, there's a minus sign. Then I use this. Then I use the antisymmetry once again. So it is linear with respect to constants in f, linear with respect to constants in G, and antisymmetric. These are all its properties. Antisymmetric bilinear. Not bilinear form, because it is something involving differentiation. So bilinear form generally means you have vectorial quantities, linear quantities, and something algebraic in them using typically a matrix. So I am coming to the derivation law. Let me write it, and then you will see it's not a good thing to think of it as a bilinear form. If you like, call it a bilinear expression, because it involves derivatives of f and derivatives of G, first derivatives. In other words, you can, as you can easily see, if C is a number, not a function of Q and P, its Poisson bracket with everybody is 0, because the derivatives of C are 0. So now this derivation law, how many of you have heard of it and how many of you have seen it? One must be the subset of the other. I don't know which way it goes. Has any one of you heard of the derivation law? Yes or no? You must. Yeah. Anybody else? It's also called the Leibniz law. What do you think it looks like? Huh?
Poisson bracket of Fh with G.
Poisson bracket of
Fh with G.
Fh, the product Fh. Yeah. See, I must also overall save time. So it's good to have these exchanges, and then at some stage I step in and say, boys, here is the result, girls, here is the result. Okay. This is called the derivation law. It's also called the Leibniz law. The structure, it looks like an algebraic statement, but this captures the idea that it involves first partial derivatives of the functions appearing in the Poisson bracket. So that's why I should not call it okay. And then there is a physical reason why derivation law should be present, but we can take it up later. Then there is a Jacobi identity. It says, suppose you have three functions chosen independently, and you take the second Poisson brackets and sum cyclically f with G, the result with H, G with H, result with F, H with F, result with G. This sum is identically 0. Okay. So, this is something that I will not prove. It involves a little bit of algebra, not too much. I leave it as an exercise. So, I will just make a comment here. Why is it important to have the derivation law? Those of you who have studied quantum mechanics know that for commutators also same kind of thing holds. These are the things that Dirac exploited. The reason why we need the derivation law is because the rate of change, the equation of motion for a product of two quantities, what is it? It's a sum of two terms. What's the first term? df by dt times g. And the second term, then the other one. Now, if the equation of motion is of the Hamiltonian form, put it in for each of the d by dt's, what is the result? It's the derivation law. So, now this is often called the Leibniz law, right? First derivative of a product is the sum of two terms. That's why this derivation law is sometimes called the Leibniz property. Okay. Now, there is another bracket in mechanics called the Lagrange bracket. It is important in certain respects, but I will not go into it here. Okay. Now comes the discussion of the transformation properties of things. Now, you will find that this Poisson bracket plays such an important role in, I mean, it is like an actor simultaneously playing many parts in a play. That's the way I can put it. You will see in a little while. I can tell you in advance, just to keep your interest up, the Poisson bracket is the starting point for determining what are the transformations in phase space which preserve Hamilton's equations in their form. That answer to that question comes from the Poisson bracket. So, Poisson bracket tells you what are the transformations we should be looking at. Those are called canonical transformations. Then the Poisson bracket shows you how to construct those canonical transformations. That's very interesting. It not only first helps you to define the transformations of interest, having done that, it takes on the next role. It shows you how to construct such transformations. Okay? So, this is, I think, something very important. And then it turns out this Jacobi identity, which presumably was discovered by Jacobi, it is something which reappears in the mathematical theory of Lie groups. I will not go into it in this lectures, but the Jacobi identity is a key ingredient in the representation theory of so called continuous groups in mathematics. That has a lot of relevance for physical applications in different subjects in different ways. And so, my impression is that my guide Sudarshan got the spirit of these ideas from his association with Julian Schwinger, that there is such a great connection at a deep level between the theory of Lie groups and the structure of classical Hamiltonian dynamics. And so, together we wrote a book many years ago. How many years ago? 1974. How long is that? 44 years? Too old. Too long ago. Okay. So, now I come to the covariance properties. What we have seen is that in the Lagrangian formalism, let me try to draw a picture of configuration space. A point transformation is, see, the older physics books even Sommerfeld for that matter, take a somewhat loose attitude towards the use of these terms. A point transformation is generally thought of as a replacement of one set of generalized coordinates by another set of generalized coordinates. So, in that spirit, if you say I do not want to describe particle motion using Cartesian coordinate x, y, z, but I want to use spherical polar coordinates r, theta, phi, there is a tendency to say, yeah, that is a point transformation. You are replacing x, y, z by r, theta, phi. But you must be careful to understand that is not interpretable as a point transformation acting on a given configuration space. Okay. There is some sophistication involved here. For a single particle motion in 3 dimensions, what is configuration space? It is Euclidean 3-dimensional physical space. Now, you can describe, take an origin, take Cartesian axis. Each point in this configuration space can be described by its x, y, and z coordinates, or it can be described, if you wish, by r, theta, and phi. But that transition from x, y, z to r, theta, phi cannot be pictured or interpreted as a mapping of x, y, z Euclidean space onto itself. No. A rotation, yes. A translation, yes. A Galilean transformation, yes. But not the switch from Cartesian to spherical polar. But in the older physics way of writing, everything is called a point transformation. So, this is something, it is fairly subtle point, but I want you to keep that in mind. So, anyway, a point transformation, if you want to be more correct, should be thought of as a one-to-one onto mapping of configuration space onto itself. Every point in configuration space under the point transformation goes to some image point. The image point q prime comes only from one source point, that is the one-to-one nature. While q prime is written as a function of q to describe the point transformation, it has an inverse. Q can be expressed as a function of q prime. So, all these properties are understood to be present. So, what we can say is that, let me write this a little bit in detail. The old equations of motion, by old I mean in the q variables, this system of equations for all the degrees of freedom as we have seen yesterday, it can be stated through Hamilton's principle of stationary action. Now, so that gives it a very succinct expression. Then what happens is that inside the action functional, instead of using variables q, use q prime. So, what will happen is that action principle in words remains unchanged, but the explicit form for the action in the new variables has a new shape, you can say. But the idea that there is a action functional and the fact that nature behaves so that the action is stationary, all that remains true. So, I will just omit the steps mentioning the action functional, but they are there in the notes which I think are available to all of you. It is equation number 63, and let me just write it in this way. You make any point transformation you want. Choose this mapping of configuration space onto itself in any way you like. Given a starting Lagrangian, which is a function of given to you q and q dot, there is always a way to define a new Lagrangian, namely by what I am now writing. so that the old equations of motion as a collection of equations of motion have the same physical content and meaning as this new set. This is what we mean by saying that the equations of motion second order dynamics in configuration space written down by Lagrange, they preserve their form under all point transformations. Okay, I hope that is clear. Now, I can rub this board and describe the Hamiltonian situation here. Numerically they are equal. See, q prime is a function of q, but it is invertible. So, if I wish, I can express every q as some other functions of the q prime variables. So, I take the original Lagrangian in which q1, q2 up to qn appear and q1 dot, q2 dot up to qn dot appear, express all of them in terms of q primes and q prime dot. Then do whatever algebra, rearrange, cancellation, etc. Whatever is left at the end is called a L prime. The prime on L, what does it mean? What does it mean in words? Form. Functional form in general can be different. In case L prime as a function happens to be the same form as L, you would say you have a symmetry property. The Lagrangian has not changed in its functional form. Anyway, you do any point transformation you want. Here is a rule to replace the old by the new Lagrangian. The new equations of motion have the same physical content as the old equations of motion. Okay? They may look different, but the structure is Lagrangian type. It is what you would get from Hamilton's principle of stationary action written in the q prime variables. Now, what is the analogous situation in the case of phase space? See, maybe I'll use this part of the board also. What Hamilton showed was that with every configuration space there is associated a corresponding phase space which is double its dimension. If capital Q is dimension n, the number of degrees of freedom, its phase space has dimension 2n. So naturally I should draw it a little bigger. The phase space corresponding to Q, I don't know what the older notations was. It was called gamma, I suppose, capital gamma, which is the notation used in statistical mechanics. But today's mathematical machinery calls it the cotangent bundle of the configuration space. I will not go into the details of this mathematical development. It's very, very beautiful, and at some stage you should learn it. After all, we are in the 21st century. I must bring it in. But I just want to make a passing comment and then continue. The comment is the way in which Hamilton introduced canonical momentum variables, p variables, was to say, given a Lagrangian, for each of the generalized coordinates in the Lagrangian, he defined a corresponding canonical momentum. So this gives you the feeling that to introduce canonical momentum variables, p variables, and they are said to be conjugate to q. This is just terminology. It gives you the feeling that you must be given a Lagrangian. It gives you the feeling. If it doesn't give you the feeling, you are a very advanced soul. I can say. But traditionally, the way we were taught is that unless you tell me what the Lagrangian is, I don't know how to set up canonical momentum. This was the old fashioned way. This is the way I learnt classical mechanics. And going back to TIFR, I learnt classical mechanics from Professor Virendra Singh in a set of lectures over 3 weeks in the training school, 1958. How many years ago is that? 60 years? 60 years. The anniversary of that. So it gives you that impression, and certainly we all grew up thinking so, that in order to define momentum concept, canonical momentum concept, you need to have the Lagrangian. You must know what the Lagrangian is before you know what momentum means. This was the feeling. Well, much water has flowed beneath the bridge. Today, when you learn the mathematics appropriate to classical mechanics, for example, Arnold's book or other books called Abraham and Marston, so many advanced books, you learn that given a configuration space, automatically a corresponding phase space can be created. It is double the dimension of capital Q. It is written in this way: if this thing is dimension small n, this thing is dimension 2 times small n. The creation or the definition or the existence of a phase space for a given configuration space does not require knowledge of a Lagrangian. That is a very important message I want to say. Some of you may know it, for some of you it may be new, it may even be hard to believe. But this is strong medicine, you must take it at some stage. I mean, this is a modern way of doing things. Now, my whole course is in the old fashioned language, but wherever possible, surreptitiously I should slip in some of the modern points of view. So, I want you to appreciate the momentum variables are there in a mathematical sense, not in a physical sense, once you tell me what capital Q is. I don't need to have the Lagrangian. But now I will go back, I will slip into the old way of talking. I will say, here is a Lagrangian and here are the corresponding canonical momentum variables. So, I will have this Jekyll and Hyde character. I will use this when I want, I will use that when I want. You can never catch me. Right? So, this preservation of the form of the equations of motion, this was in the Lagrangian version, and for it the basis was configuration space, and I have told you enough about it. Now, let us ask the analogous questions for the Hamiltonian system. So, first I will write the system of equations of motion for a given Hamiltonian. There is one, they are all first order differential equations in time, and there are 2n equations now compared to n Lagrangian equations of motion. All this is clear. So, now the question analogous to the previous one is the following. Given a Hamiltonian which is a function on phase space, and given these equations of motion in Hamiltonian form, suppose you imagine that you have a 1-to-1 onto invertible mapping of phase space onto itself. Okay? After all, the word is the arena for Hamiltonian mechanics is the phase space. So, the question analogous to the previous one will now be, if I imagine instead of a point transformation, a map of the whole phase space onto itself, point q p in phase space being mapped to q prime p prime with the property that it has an inverse, that is, the transformation mapping itself gives you q prime as a function of q p, p prime as a function of q p, and you are able to invert. You are able to express q and p in terms of q prime and p prime. So, if I give you any such mapping, can I suitably redefine the Hamiltonian? can I construct some, this is a question now, question, is it possible to find a Hamiltonian in one way or the other such that the same physical content, the old equations of motion can be written again for a suitable choice of new Hamiltonian using the Poisson bracket idea. Is it, so you give me some definition of q prime p prime in phase space in terms of qp. It must be possible to invert it. If the q and p evolve in time by this set of equations, and I give you the mapping qp to q prime p prime, is it true that I can always cook up a new Hamiltonian as a function of q prime p prime such that the same physical content of the old equations of motion can be expressed in this form? What does this form mean? It means d by dt of q prime equals partial derivative of h prime with respect to p prime. d by dt of p prime equals minus partial derivative of h prime with respect to q prime. Question, is it possible? Remember, we said at the Lagrangian level, it is always possible, given any point transformation, to find a suitable new Lagrangian, and the equations of motion will preserve the Lagrangian structure. So it's the same similar question which I am asking, not the same question, analogous question in the Hamiltonian form. Okay, so what is the answer to this hypothetical, to this question? Answer is no. Okay. If you cannot say that any change of variables in phase space will preserve Hamilton's equations of motion. You cannot say that. For the Lagrangian, you could say any change of variables on configuration space preserves the Lagrangian structure of the equations of motion. You are always able to find a suitable new Lagrangian so that the old equations reappear in this form. That is not true in phase space. So this is fairly yeah, I am coming to those conditions. So what are those conditions? So please read the notes which have been given to all of you. I have written here, a little thought will show that the answer is in the negative. So please supply that little thought. So the answer to the question is the following, as you anticipated. If you are given a mapping of phase space onto itself, and if you want to ensure that it will be possible to find a new Hamiltonian, so that the equations of motion retain the Hamiltonian structure, then this mapping must obey a whole lot of restrictions. Those which are allowed by this criterion are called canonical transformations. So I just want you to absorb this lesson. At the level of configuration space, all point transformations are allowed. They will not harm the Lagrangian structure of the equations of motion. At the level of phase space, a similar statement is not true. Only particular kinds of changes of variables in phase space will preserve the Hamiltonian form of dynamics. Those transformations are called canonical transformations. Okay. Now, so I will now describe those canonical transformations, the ones which are such that they allow you to construct a new Hamiltonian. You can put it in words in that way. So There are two sentences which are here, my equation 66 of the notes. I will just read them out rather than write, because they are accessible to you. And these are repetitions of what we have been saying in so much detail. So, first of the Lagrangian equations of motion, we say the covariance group of Lagrangian equations of motion. Covariance group, it means transformations which preserve the structure of Lagrange's equations, is the group of all point transformations on configuration space. No restrictions. The group concept we discussed briefly yesterday. You take one mapping, one point transformation, another one, you compose them as maps and so on. So, the covariance group of Lagrangian equations of motion is the set of all point transformations on capital Q. There are no conditions except it should be invertible. The change of the Lagrangian can always be calculated so that the equations are preserved in structure. Now you come to the Hamiltonian. The statement is the covariance group of Hamiltonian equations of motion are those transformations QP to Q prime P prime which maintain the structure of the Poisson bracket. So, here is the role of the Poisson bracket. Exactly what it means, I will write equations in a minute. So, if this mapping preserves the structure of the Poisson bracket, explain it soon, then and only then a new Hamiltonian can be constructed, and the equations of motion will maintain the Hamiltonian form. So, the group of such transformations is called the group of canonical transformations on phase space. Okay. Now, there are some trivial exceptions to the statement I made, but we don't have to spend time on them. All right. So, now I am going to write the conditions. So, already you know that the Poisson bracket has appeared when we wrote down the Hamiltonian equations of motion. Then I listed its most important algebraic properties. Now is the second role of the Poisson bracket. It tells you what phase space transformations preserve Hamilton's equations in structure. The transformation must preserve the Poisson bracket, because the Poisson bracket tells you what the equation of motion is. Yeah.
Is this transformation so
Which
rigid? Because
rigid in the sense?
rigid in the sense much more constrained, like limited. So many conditions have to be considered.
Yeah, yeah. I'll write the condition. Yeah.
In phase space, if there are two non-intersecting trajectories,
Oh my God. Yeah. Yeah.
canonical, then any sort of transformation might.
No,
be
that cannot. Such things cannot happen. Such things cannot happen. Those things they have a topological flavor, right? So, canonical transformations preserve all those properties.
I'm saying that we cannot. Is that one of the reasons? That
No. The things that I am going to describe were discovered 150 years ago, roughly speaking, much before the more recent discussions of dynamical systems and so on. So, you said much more rigid, So, so I have to tell you what conditions must a phase space transformation obey to be called canonical. I will tell you in a moment, but true, you cannot think of any mapping of phase space and say, it is going to preserve Hamilton. It will not. However, every point transformation of the Lagrangian theory reappears as a possible transformation in phase space, and it will be canonical. So, this group of transformations is a subgroup of the group allowed here. Here, everything under the sun is allowed. Here, lot of restrictions. Even so, and that is what you meant by rigid, the group of all canonical transformations is immensely larger than the group of all point transformations. You must keep these ideas in mind. Huh? Very important. So, everything here will reappear here, but many more are allowed here. That is the point. Even so, there are conditions, but remember, this is twice the dimension. So, there is, like people say, there is lot of room in Hilbert space, like that kind of thing. There is lot of room in phase space. Okay. So, this is the relationship between the two. Okay. So, since the notes are accessible to you, I may here and there, to save time, skip some of the things which are described in detail. So, I will give you two definitions of a canonical transformation. Two definitions. There are three actually, they are all the equivalent to each other, but I will give you only two of them. The first definition of a canonical transformation. It says, write every q prime as a function of qp, every p prime as a function of qp, then calculate the Poisson brackets of the q primes and p primes with one another. Then the conditions are q prime r, q prime s equal to 0, these equations, the fundamental Poisson brackets must not change their values. So, it is understood how are you to calculate these Poisson brackets. Write every q prime as a function of qp, every p prime as a function of qp, and use the definition for calculation of Poisson brackets in terms of qp. Partial derivative of q prime r with respect to some q, of this one with respect to the conjugate p minus, and sum over all the degrees of freedom. So, this is definitely a lot of restrictions. So, you can easily construct a transformation which does not obey these things, very easy, okay, so easy. All right. So, we say this way of defining the conditions for a phase space mapping to be a canonical transformation is the preservation of the fundamental Poisson brackets. Now, in quantum mechanics, which you have already, all of you have studied, we say the fundamental Heisenberg commutation relations, canonical commutation relations, are preserved by unitary transformations. So, where does all this come from? From this classical background, at least in the work of Dirac mainly and many others also. The inspiration, the way to set up the machinery of quantum mechanics was, it was a great inspirational work. So many times I say in general talks, it is still amazing to imagine that these three people in a 2-year period were able to discover the structure of quantum mechanics. Today we have discussed it for almost 100 years. Still everything is not understood. The interpretation, there are problems. But the very fact that such a coherent, clear-cut mathematical framework was extracted from their ideas and experiment at that time, it remains a real marvel, right? So, that goes of course into quantum mechanics. So, this is the first definition of a canonical transformation. The second definition of a canonical transformation, see, there are some additional things in my notes following this first definition. Incidentally, just for completeness, let me mention in my notes, this is equation 67. Now, I come to definition 2. The transformation from one set qp to another set q prime p prime is a canonical transformation if and only if this differential expression p prime dq prime minus p dq summed over the different degrees of freedom, the p of every degree of freedom times the differential of its corresponding q, new minus old, this in the language of mathematics should be an exact expression. And what does that mean, exact? It means it must be the differential of some s, some function on phase space. Okay. So it is really quite amazing and really very pleasing that the definition of a canonical transformation can be given in such an elegant and succinct form. One equation, not a system of so many Poisson bracket relations. How many relations do we have? We have n squared here. We have half n into n minus 1 here, half n into n minus 1 here. So what's the total number? 2n squared minus n algebraic statements here. In all of them have to be satisfied. All of those conditions can be collapsed into one equation, one line, and that is the second definition. Okay. So you have to look at it, play around with it to really feel that yes, this definition is entirely equivalent to the first definition. And you can see that the second definition is in many ways very, very I don't know what to say. It is so compact. Okay. So if a transformation on phase space does not obey these conditions, you call it a non-canonical transformation. You will not consider it because it will not allow you to retain the structure of Hamilton's equations of motion. If these are satisfied, all is well. I might just say here, in the case of a point transformation, how does it reappear as a canonical transformation? Let me just show you that. Just a simple equation here. For the case of a point transformation on configuration space, where every new coordinate variable is a function of the old coordinate variables, any set of functions are allowed provided it can be inverted. All you have to do is to transform the p's in this way. Here I have written partial derivatives of q with respect to q prime. This means I am using the assumption that given every q prime as a function of all the q's, in principle that can be inverted, and I can write every q as a function of all the q primes. That set of expressions is needed to see how to transform momentum. So every point transformation on configuration space leads in an unambiguous way to a canonical transformation on phase space. Those are the equations, and now it's a matter of little bit of algebra to check that all of these things are satisfied. I will not do it, but it's a challenge if you feel like doing it. Much simpler is to use the second definition. Much simpler. Plug this in to this expression. What do you get? P prime dq prime minus p dq. Do you see that it is an exact expression? I say it is actually 0. It's a small calculation, a little bit of a challenge. You will find things just cancel. So it is a canonical transformation because I said this is an equally good definition of a canonical transformation. It's the case where S happens to be 0. That's allowed. Okay. So this is the sense in which all the transformations of Lagrangian mechanics, point transformations, reappear among phase space canonical transformations.
So where does this thing come out? For example, the Jacobian of the transformation is the determinant of the Jacobian is +1.
For the phase space transform. Yeah. Yeah, it can be derived from here, it can be derived from here. All of these are.
So once I say the first one, let's say, so I don't have to say it again that the Jacobian has determinant 1.
It can be derived from here.
So this is the basic.
Yeah. The interesting thing is that this definition of a canonical transformation is completely identical to the second one, but see how differently they are expressed. So I think one has to develop a kind of mathematical taste, you can say. This thing, for me, every time I see it, I feel a thrill. Such a simple statement, such a simple, and it has as much conditions as all of these things. Okay, so this is very important, and this many of you teachers try to communicate it to the next generation, your students. Let it not be lost. That's the main thing. Okay. Now I will make a few comments about the relationship between these two. The second definition says a certain differential expression. In modern mathematics, it is called a one form. It should be exact. It must be the differential of something. Now, things like this, I think, relations or statements of this kind keep appearing in thermodynamics, for example. So it's not totally alien to other parts of physics, but this is in the context of mechanics. Now, this S can be any function on phase space. Now, I make some statement, I won't write it down. Suppose you decide you will express this function S as a function of Q's and P's. Certainly possible, because Q's and P's together form a complete independent set of coordinates for phase space. So I can imagine that I write S explicitly as some function of Q's and P's in this second definition. All right? Or Q prime and P prime. No problem. You will find, if you work out the consequences, you get back definition 1. This is a very instructive exercise if you have not done it. Even experienced people may not have worked it out. I would like you to devote a little time, convince yourself this is one way to show definition 2 and definition 1 are one and the same. 1 and 2 are one and the same. All right? Or you can say, I will think of it as a function of Q prime and P prime. So if this function S is imagined, written explicitly in terms of the QP variables or the Q prime P prime variables, do a little bit of work with this second definition, you'll get back all of definition 1. Now comes a very interesting, yeah. Yeah. Sorry? Yeah. Yeah. No. See, the statement says there should be a function on phase space such that the left hand side is the differential of that function. So wait, at the definition level, I have not said how this function S should be written. I have not said. You are anticipating what I am now going to do. Exactly what you said I will do now. You are happy? If I imagine that S, being a function on phase space, is written in terms of Q prime P prime or QP, which it certainly can, because those are valid systems of coordinates on phase space, you get back statement 1. That's what I said. Now I come to what you said. Here is an alternative. Supposing in a particular situation in a particular canonical transformation, supposing the set of variables qr and q prime r, the old generalized coordinates and the new generalized coordinates. How many variables are there? There are 2n of them. Suppose they are all algebraically independent. Suppose. It means that any function on phase space could be written as a function of these variables. This is what you are saying. But there is an important fact to remember. The collection of variables q and p, the old coordinates and their momenta, are set to form a you can say for the moment canonical coordinate system for phase space. Some variables, coordinates and their conjugate momenta. So it's a canonical system of variables, coordinates on phase space. This is another canonical system of coordinates on phase space. Any phase space function can be written in terms of qp or in terms of q prime p prime, which is what I just described. Supposing in a particular situation, it turns out that the old generalized coordinates and the new generalized coordinates are also mutually independent 2n variables. They will be a non-canonical system of coordinates for phase space. They are not like certain generalized coordinates and their momenta. They are some old coordinates and some new coordinates, all the old coordinates and all the new coordinates. Supposing a transformation is such that these are all independent. In that case, as you said, I can certainly imagine writing the function s as a function explicitly of new coordinates and old coordinates. So it is possible only if the transformation involved obliges. The mapping, the change from qp to q prime p prime must be such that this part of the old canonical coordinate system, this part of the old coordinate system, the two together must give you a non-canonical way of describing phase space. Enough independent variables, but they are not conjugate pairs. If that were so, for such canonical transformations, I can imagine writing this s as explicitly a function of q prime and q. So let me repeat. Writing s as a function of qp, always possible. Always possible. Why? Because by definition qp are coordinate system for 2n dimensional phase space. Writing it as a function of q prime p prime, again always possible. But such ways of writing s give back definition 1, nothing more. Just go back to the first definition. If in a particular case you have this kind of non-canonical description of phase space possible, then I can imagine writing this function s in terms of those variables, not q and p or q prime and p prime, but q prime and q. In that case, what happens to this equation? You can read off these equations, right? So let me put back the arguments here. Now you have a beautiful result. Choose any suitable capital S. It has to obey a condition. I come to it in a moment. For any choice of an allowed capital S in this form, here is a canonical transformation. The second definition, when expressed in this manner, allows you to describe canonical transformations. So the definition is giving you a route to the construction. That's the way to put it. What is the condition on the function s that I must impose. Look first at this set of equations. This is old momentum, old coordinate. This subset of equations must have a structure such that you are able to invert them, express every q prime in terms of qp. That must be permitted by S. There is a Jacobian condition for S. I'll leave it to you to guess what that condition is. Suppose S is such that this part of the equations allow you to express every q prime in terms of q and p. Take those expressions, plug them in here. Then you get p prime in terms of q and p, and you are done. So the beauty of this second definition is that for certain canonical transformations, you have an explicit, not explicit, I think, what is it? No, implicit, I suppose. You have a way of describing an actual canonical transformation. Choose any S obeying a certain condition, and then here is the canonical transformation. So, can anybody guess what is the condition that the function S must obey? What is it must allow? It must allow you to invert these equations and express every q prime in terms of qp. The number of equations is correct, there are n of them. So what is the condition on S? Anybody want to guess? It's a Jacobian condition. Yeah. Yes? Yeah, exactly. Very nice. So I'm very happy you said this. This is the condition. This is the kind of thing that comes up in mathematics where you talk about implicit function theorem and so on. So now I can complete the story. You have coordinate variables q and p in phase space. You don't know, you want to construct an allowed transformation, a canonical one. You don't know yet what q prime and p prime are. Here is the recipe. Choose any function S of at the moment unknown q primes and q, obeying that Jacobian condition. Then these equations give you an allowed canonical transformation. Okay? All right, this is clear. So just a comment that it was exactly this kind of S of old and new coordinates which was used by Dirac in his 1934 paper. I referred to it on Monday, the starting point of Feynman's path integral approach to quantum mechanics. It was the analog to this which Dirac discovered in quantum mechanics. And he said, he did not say they are the same. He said there is something in quantum mechanics analogous to this in classical mechanics. And the story goes, Feynman said, why do you stop it saying they are analogous? Can you say that they are the same? Or can you bring them closer? And he brought them closer, and it ended up with his path integral formulation of quantum mechanics. So the ideas are very, very deep and very beautiful. So any choice of a function S of old q and new q prime obeying this Jacobian condition is permitted, and it will lead to a canonical transformation through this system of equations. Some algebra is involved to get explicitly q prime p prime in terms of qp. Okay. Now I come to something which Shamik asked the other day in private conversation. In the older books, people say we can imagine some other forms of this kind of description of a canonical transformation. Supposing that we imagine, well, I will write everything down. in the old editions of Goldstein, I don't know about the newer editions, they would say that you can generalize it to 3 other options, 3 other possibilities. Suppose you have a canonical transformation for which the old momentum and the new coordinates are all mutually independent. You can imagine modifying the second definition and describing it completely with a function S of this variety. Another option is old coordinate, new momentum, old momentum and new momentum. So, in the old days people would write there are 4 ways of describing a canonical transformation in this spirit, and they are all called generating functions. Generating functions. This S is called the generating function for that canonical transformation. So, you can write out easily the replacements for these equations in each of the other 3 cases. So, now the interesting thing is, and I think you mentioned this. So, I was taught and people were taught in my generation, there are 4 types of generating functions, 4 ways in which a canonical transformation can be built up through the definition 2. Okay. Of course, it goes without saying, once it is constructed, it will obey all the conditions of definition 1. No worry about that. But you can easily construct for a system of, I think in the notes there will be there a simple example where none of these will work. None of these 4 will work. Incidentally, suppose I go back to this point transformation. Q primes are functions of Q's. This will not work. Correct? It's clear. So, it is easy to write down a simple canonical transformation. I think it's for 2 degrees of freedom. You can check my notes where this will not work, this will not work, this will not work, this will not work. All 4 will not work. Because for that canonical transformation, none of these 4 combinations of half old and half new give you 2n independent quantities. They don't. Okay, so then you ask, does it mean that you have to give up, for such cases, you have to give up the idea of a generating function? The answer is no, and I will complete today with stating a very beautiful theorem of Carathéodory. Now, you know which Carathéodory? Thermodynamical Carathéodory. He was a mathematician, and I think it was Max Born or somebody who challenged him to give a new statement of the second law of thermodynamics, and he came up with a very deep, profound way of doing it. That is described in Chandrasekhar's book. Which one? Radiative transfer, one of those books. Constantin Carathéodory. So, I will just describe his result and then I will stop for today. I think it's a very beautiful result, and I sincerely hope you think so too. Okay. So, the theorem goes like this. Let us list all the variables under discussion. Here are the old variables. We say the original phase space variables are n mutually conjugate pairs of variables, every q and accompanied by its p. All right. Then I write here are the final mutually canonically conjugate pairs, every q prime along with its partner p prime. Now here is Carat-Theodory's theorem. It says out of the first old pair, choose any one, either the q1 or the p1, choose any one of them. Out of the second, choose any one you like, q2 or p2. That means out of each old pair, choose either its q or its p as you wish. All right. How many choices do we end up with? No. 2 to the power n. The same 2 to the n which appeared in Feller's calculation. How many choices? 2 to the power n choices possible. One out of each pair you choose. Canonical pair you choose as you like. Then the theorem says for any choice which you make here of this kind, there is a way of choosing one out of these two, one out of these two, one out of these two. So n variables here and n variables there, so that all together you have 2n independent phase space quantities. Just incredibly beautiful result. Okay, that is Carat-Theodory's theorem. And for every such choice, there is a description in the language of generating functions. It is not true that these are only 4. It is not so that some canonical transformations cannot be described in this language. Everyone can, in at least 2 to the power n ways. Just this theorem of Carat-Theodory, there is a set of 2 books called Partial Differential Equations and Variation Principles or something like that, published in late 1950s or something like that, 50s, 60s. If I have read it, it must be half a century old. And it is by Carat-Theodory, volume 1 and volume 2. And I remember the publisher's name at that time, Holden Day in San Francisco. Today, with a suitable mobile, you can check if this is true or not, which edition and all that. In one of those, volume 1, I think, this theorem is proved. It's called Carat-Theodory's theorem. I feel it's a very beautiful theorem, very nice, important theorem, tells you so much about canonical transformation theory. So I will stop here. Yeah, it is time. As I said, there is a third definition of canonical transformations in the language of what is called Lagrange brackets, but I will not go into that. So what I will begin tomorrow is to describe the group theoretical properties of canonical transformations and then go on from there. Okay. So again, preview of coming attractions. This S I called generating function, and it turns out for many physically important cases, the action which appears in Hamilton's principle leading to the equations of motion of a mechanical system, that action at the end of the day becomes this function. So the whole subject has, I don't know what to call it, such an integrity about it. Of course, it's an old, well-established subject. Only the best results have survived. That is also true. Many things must have been found which have been forgotten. But let us hang on to these gems, I would say. So I will describe tomorrow the group properties of canonical transformations, the covariance of the Hamiltonian equations of motion, and then this part, the role of the action in this whole story. So one thing we have seen, the canonical transformation, I gave 2 definitions. Definition 1 in terms of Poisson brackets, definition 2 in terms of this differential expression. The second one we exploited to bring out a way of constructing canonical transformations. So, the definition leads to a way to construct them, and this Carat-Theodori theorem completes that development. Now, tomorrow I will go back to the first definition basically and show the Poisson bracket plays two roles. The first one defines when is a transformation a canonical transformation. Second one I will show today, through the Poisson bracket you can construct canonical transformations. So, there is a movie of 1957, I think. I don't know if anyone of you has seen it. It's a charming movie, one of Danny Kaye. Who has heard of Danny Kaye? Who has not heard of Danny Kaye? You have not heard? My God, your culture is sadly lacking. So, he was one of the greatest comic actors of that era. There is a film called Me and the Colonel. It's a beautiful story by a Hungarian writer, I think Franz Werfel, very charming. It was no, not Mistaken. No, that is one of his other movies. So, in that, the phrase which always keeps coming, it is set in the period of the Second World War when Paris was captured by Germans and he is escaping with others. And in every difficult situation, he says, my dear mother used to say, in life there are always two possibilities. And that phrase keeps on coming. So, in that spirit, you have two ways of defining canonical transformations, and each one of them acts as a definition and a method of construction. Okay? Please appreciate that point. So, let me stop here.